Today I'd like to talk about data structure lower bounds for various computational models. So we'll try to see what we can prove, and we'll try to prove barriers, at least some conditional barriers for the things that we cannot prove yet. Okay, so it's a talk about data structures, but in the last few days, we're mostly looking at dynamic data structures. So in the next 10 slides, I'll be repeating that we're only working with static data structures. So static data structure means you're given the input once and forever. It's never going to be changed. You have unbounded preprocessing time to preprocess it. And then I want you to quickly, efficiently answer the queries. So one example is a Google Maps problem where I'm giving you a big map. It's essentially static, you have a couple of weeks, all the power of, of Google to preprocess it. So you effectively have unbounded computational power here to preprocess it. Once you're done, I want you to quickly answer queries. What's the shortest path from here to there? Nearest neighbors is another example. I'm giving you a bunch of cluster centers. Spend as much time as you want to preprocess them, but then quickly answer queries. I'm giving you a point what's the closest or one of the closest cluster centers. And a problem that we'll be looking at today, many times, is a range counting problem. Again, I'm giving you many, say, shapes, maybe like rectangles. You have a lot of time to preprocess them, but then quickly answer the queries, like how many points do you have in this rectangle, how many points you have in this rectangle, and so on. Okay, so once again, the input is given to you, you preprocess it, and here we place no restrictions on your computational power. But then once it's the query phase, please quickly answer every possible query. You know all the possible queries in advance, you know all pairs of cities in the world. So when you design your data structure, you already know all queries that will be asked. And you need to come up with an efficient data structure. Okay? Pictorially, a data structure, a static data structure looks as follows. You have n inputs from your favorite domain. Then you preprocess them into some S memory cells. The preprocessing is unbounded. So typically, S is greater than n because you don't want to lose information about the input for most problems. And then you answer each query efficiently. So maybe you look only at T memory cells or you perform only T operations. I want this query phase to be efficient. M, the number of possible queries, the number of possible, say, pairs of cities is known in advance. All queries are known in advance. And M is typically polynomial in n, possibly like a huge polynomial in n, maybe n to the 100. All right, so we'll say a data structure is efficient if it uses essentially optimal space, say linear in n, and its query time is reasonable, say polylog n. Okay? So, yeah. Okay, in this tutorial, we'll be looking only at static data structures. Also, there are like a bunch of parameters. M, the number of queries, S space, T time, word size, field size. And Ho Chen on Monday, in his first part of the tutorial, did a very good job tuning all of the parameters, proving optimal lower bounds for every setting of the parameters. The focus of this tutorial is different, so we'll first get rid of most of the parameters just to simplify the model, and we'll work under the following simplifying assumptions. So all inputs, memory cells, queries, outputs, everything are going to be elements of some finite field f. In particular, we don't have any cell size, word size anymore. Everything is an element of some finite field. Okay?
Would the size of the field be relevant?
Sometimes, yeah, but yeah, but not much. Up to log factors and the field size or something like this.
So the query time here is how many elements of the field do you use?
So on the next slide, I'll just explain the outline of the talk. We'll be looking at different models of data structure, and for each model, it will be clear what we mean by running time. Yeah. Then the number of queries is always polynomial in n, so log of m is always linear in log of n. Okay. And for simplicity, we'll be only looking at non-adaptive data structures. Many, or at least some of the results I'm presenting can be generalized to adaptive data structures, but that's not the focus of this talk. So please do feel free to ask questions what can be generalized to non-adaptive, to adaptive data structure lower bounds. But by default, we'll be talking about non-adaptive data structures. Amir?
The number of queries means the possible number of possible.
Right. The universe of all queries, you know them in advance when you design the data structures. It's essentially all pairs of cities in the world. So it's kind of n square, maybe. Yeah.
That gives the lower bound the field size, no?
Not necessarily. For polynomial evaluation, it does. But for other problems, maybe a query is a pair of elements from the field. Yeah. Okay.
Is it crucial that M is wholly M?
It's not, but usually, like in lower bounds, you would have something like log of M, which is another parameter, and we don't want to have another parameter. We'll essentially be working with S and T, space and time. W, we get rid of assuming that memory cells are exactly of the size to field your elements of the field. And yeah, M we get rid of by saying that M is fully affine. Okay, so that's what we're not doing in this talk. What we're doing is we're looking at different computational models. So the first model is cell probe model. Here the running time, the query time, is measured just by the number of memory cells you're reading. This seems to be the strongest model. Once you prove a lower bound here, then probably it applies to all reasonable models, all realistic models of data structures. Yeah. But yeah, possibly because this model is so strong, we can't prove very strong lower bounds either. We would like to prove lower bounds on something closer to running time of the query phase. For example, yesterday Casper in his tutorial showed a very efficient cell probe data structure for OMV or UMV, and less efficient data structure when you actually measure the running time. We would like to design some techniques that could, some lower bound techniques that could differentiate between the two. We still don't know how to do this, but yeah, that's the goal. So in weaker models of computations, we'll just give less power to the query phase and see if we can prove stronger lower bounds. For example, we can consider linear model. Here, my problem, every output is a linear combination of the inputs. But I only allow you to compute linear combinations in your data structure as well. So all what you can do are linear combinations. That's weaker than the cell probe model. Can we prove stronger lower bounds at least here? It's actually conjectured that for linear problems, linear data structures should be essentially optimal. So if you prove a lower bound here, then it's conjectured that for the same problem, it should extend to models like this. Yeah?
Here, it's not necessary to have sort of an algebraic model, right? You could also
Yeah. You can say here you have like some restricted circuit or something. Yeah, this we essentially didn't study yet. We're looking at algebraic models, arithmetic models. Yeah. Okay, does a linear model make sense? Yeah.
The linear model means the P's are linear and the Q's are linear.
That's excellent question. So let's define it the following way. Here everything is linear. Here everything is linear. But without loss of generality, you can assume one of these layers is not linear. For a linear problem, if one of these two layers is linear, the other one is not, you can linearize the remaining.
No, that's only the one way, right? It's only the output layer is linear.
No, you can linearize this as well. Yeah. Without any loss in the parameters. You'll keep same S and T. You can linearize either of them, but not both. At least we don't know how to do both. The conjecture says you can linearize both, but we don't know how to do this. Each of them we can.
So then without loss of generality, we assume both are.
Yeah. Just so that it's easier to, for lower bounds, it's easier to.
So I'm a little, how about the adaptive versus not adaptive? I mean, because I know that in the dynamic setting, for example, non-adaptive models are much easier, right?
Yeah. So here for linear model, we'll be working with non-adaptive lower bounds on them.
I think the question was different. We know that non-adaptivity in dynamic setting trivializes. It's very easy to prove those.
Yeah.
In the static world, there is no separation. In the static world,
Yeah, we essentially almost always with some extra work can match non-adaptive lower bound for adaptive data structures as well. But it requires more work in many cases. But there is essentially no difference between lower bounds we can prove for adaptive and non-adaptive.
Sorry, so you're saying, if I understand, so you're saying that there's no separation known between adaptive and non-adaptive?
No provable separation, yeah. And moreover, the best lower. Yeah, except for
in the dynamic model, if you restrict to non-adaptive queries, then you can prove polynomial lower bounds. This is the adaptive die printing. In the static world, if you assume non-adaptivity, we don't know how to it doesn't buy you anything.
Even
You
for
just-
non-explicit functions, like there's even no separation.
So you cannot prove higher lower bounds in the non-adaptive setting, but there exists explicit problems where you can prove higher
better.
lower bounds.
Yeah, I mean, like binary
Yeah, but
search
it's not-
by
but they're still
sort
not higher than log.
predecessor.
Yeah, they're not
Like
higher.
you have to use adaptivity.
I think that's what you mean.
But you cannot surpass the log and lower bound.
Even for
It's not that
for
there's no
completely
separation.
non-adaptive.
Like predecessor search, you can prove separations.
And what is it?
Yep.
Okay.
Go.
You
Like,
can
non-
for predecessor
to
search, of
predecessor
course,
search
predecessor.
non-adaptively, you need more than log n. I would expect. Can we not prove that?
No, we don't.
No,
Yeah, we don't
no.
know how to
Oh, so but we believe it's true, but we
That's the
cannot
point.
prove it.
The Holy
even,
Grail.
even for a dictionary, there's membership queries. There's a log and low bound for non-adaptive, but not higher than that. That's what I'm
Remember, the Holy Grail is beating log n for static.
Even for non-adaptive, for that.
For non-adaptive, you don't have to do it. In the dynamic setting, because the dynamic model, if you're non-adaptive, you're really tying your hands behind your back because you don't know what. For the multi-phase problem, it's easy to see that just walking in the dark.
Good. Now we can further restrict the computations performed by queries, and we can say that we're working in the group model, where all these inputs, memory cells, outputs, everything are actually not elements of the field, but of some group, and you only have, say, black box access to the group operation. So all you can do is sum up and subtract elements of the group. You cannot even take linear combinations. I mean, previously you could say I multiply like 100 by x1 and pay only 1 for it. Now you pay a lot for it. And even a weaker model, the weakest we're going to talk about today, is semi-group model. Here you can't even subtract. You can only add things. You don't have negation. Okay, so this is the strongest model, weaker. Let's see what lower bounds we can prove in this model.
Non-negative linear.
Sorry?
How about non-negative linear?
Non-negative linear.
Right, it's like linear model, but you don't have negative coefficients and you don't have subtraction.
Let me think about it. So,
Is that interesting, or does that reduce to?
What does non-negative?
Yeah, what does negative mean over a finite field?
Over finite field, I don't know. But,
Minus x is just the inverse. Is the
well, because this is all for finite field, so it makes no sense. But
no, here we don't have the field structure anymore. We have group, and what you're talking about seems to be like.
There are
It's-
monotone arithmetic circuits compared
Yeah.
finite fields
That's true.
considered.
Yeah, that's true.
Right,
Maybe
I would
that you can.
Yeah, I'm trying to
take
state
inspiration.
this
I
as
don't
a-
remember, but I do remember papers existing.
I
Yeah.
think many of the low bounds in this semi-group is anyways you want to compute some linear combination where all the coefficients are 1 on the input, so then I guess bigger coefficients won't help you. But anyways, I think many of the low bounds that are proved there, at least of this form.
So if I understand your model correctly, then it looks like Chazel's proof of semi-group lower bounds would actually give, for the semi-group model, would actually give lower bounds what you're saying.
for small constants, let's say. If the constants are small oh no.
I think if you cannot subtract, then it doesn't matter what the constants are.
I mean, even for small, yeah, sure, even for when all constants are zeros or ones.
If the constant size is large, you pay for this in the same group.
So you can sum up. Yeah. I think it doesn't matter actually. They just say that you cannot cover. Yeah, I think for any constant.
Because I mean, it makes sense for a problem like shortest paths, where you have weights, right? And you might want to sum them, but let's say you can't allow. You can sum the weights, and maybe you can multiply them by a large constant. Maybe that helps. But you cannot subtract them, for example.
Okay. Yeah.
All right.
Yeah. All right, so this is the four models we're going to be looking at it today. And okay, that's outline of the talk. Before the break, we'll see cell prop model and linear model. After the break, we'll see group model and semi-group model. Okay, and let's start with the cell prop model. So every data structure problem admits two trivial solutions. The first one is just pre-compute answers to all possible queries. You know all the queries in advance. Then your query time is amazing. You already have an answer, just read it. But you use prohibitively much space. So recall that m number of queries is like n to the 100. And another trivial solution is essentially don't do any preprocessing, just store the input. But for any non-trivial problem, then you have to read all of the memory cells. So here T is too large. And this essentially field is about trying to understand for what problems there are solutions in between with better than trivial S and better than trivial T. And as always, a random problem actually does not have a non-trivial data structure. Essentially, the only data structures for a random problem are this and this. Once your S is less than, say, 0.9 m, your T must be at least n minus 5, and the other way around. As always, the challenge is to find an explicit problem that requires large data structures. Give a problem from a reasonable complexity class, P and P to the NP, something that requires large data structures. Okay, so the best known lower bound, and Hochin gave us a couple of proofs of this bound, has the following form. Query time must be at least log of m over n divided by log of s over n. Let me parse this. So recall that m is a huge polynomial in n. It's like n to the 100. So then when space is linear, we have logarithmic lower bound on C. When space is truly superlinear, we know nothing at all. C is at least constant, but clearly it's at least constant. So that's state of the art. Let's quickly go over like a baby version of this proof. And yeah, and then see what it gives us. I think I have one more slide first. So we'll prove this lower bound in the cell prop in the strongest model. What function are we proving this lower bound for? Say we'll prove it for any k-wise independent function. K-wise independent function is a function from n inputs to m outputs such that every set of k outputs is uniform if the inputs are uniform. So the uniform distribution on the inputs induces uniform distribution on every set of k outputs. And we have many constructions of k-wise independent functions. For example, another definition of a linear error correcting code is a thingy whose parity check matrix is k-wise independent. So you can take just any error correcting code, its parity check matrix gives you a linear function which is k-wise independent. Okay, in particular, if you take the best known codes, you'll have for linear number of outputs, you can achieve linear wise independence. And for polynomial number of outputs, you can achieve n over log n wise independence. And both of these bounds are known to be optimal. Okay, so we essentially have n wise independence over any field. For this lower bounds, we don't need that much independence. We'll, for example, prove that even square root of n wise independence is sufficient for the cell sampling lower bound. Okay, let me quickly, you have a question?
Yeah.
Let me quickly sketch the proof of this cell sampling lower bound. This is the best lower bound we have in the cell prop model. So we want to say that any static data structure computing, say, square root of n.
Try to use the
I think these two are good. I think I checked.
Turn on the lights.
shade. Any of these ones.
Okay, so we want to prove that any data structure that computes k-wise independent function must satisfy this inequality. Must have t is at least log of m over n divided by log of s over n. How will we prove it? We'll just say the following thing. So this is our data structure, and inputs as memory cells and m outputs we'll say that we can find a set of say square root of n minus 1 entries such that we can answer square root of n queries. That is, all what they probe, all what this queries probe belongs to this set. This would be a contradiction because the square root of n outputs are supposed to be completely independent, but you can recover them from fewer bits, which is impossible. Okay. Okay. How do we find such a set of memory cells that is sufficient to answer square root of n queries? We just draw, say, hypergraph. We'll have a T uniform hypergraph, which means every hyperedge has exactly T vertices in it. The vertices will correspond to our memory cells, so there will be S of them. And we have an edge of size T for the probes probed by each query. So if this query probes these 3 vertices, then I have an edge containing these 3 vertices. Okay, so I have a T uniform hypergraph with S vertices, M edges, because each edge corresponds to a query. My goal is just to find fewer than square root of n vertices that span at least square root of n hyperedges.
So you fix the input already?
Sorry?
You fix the input?
No, this my data structure gives me the hypergraph, right? Just the pattern how each query reads memory cells defines a hypergraph.
So you can do it because it's non-adaptive.
Yeah, exactly. Yeah, that's non-adaptive data structure. Okay, so once I find a few vertices that span many edges, span means all vertices of these edges belong to my set, to the chosen set of vertices, right? Then I'm done, because this exactly gives me a set of memory cells that is sufficient to answer many queries. Okay, so we just need to prove this lemma that if T is less than, say, log of m over n divided by log of 2s over square root of n, then every T uniform hypergraph
T uniform means that each vertex is a part of T edges?
That means every edge has exactly T vertices. Yeah, if some query probes fewer than T memory cells, I just say like probe a few more and ignore them. So yeah, I'll have every edge will contain exactly T vertices. So I want to say it contains a set of K vertices spanning at least K plus 1 hyperedges, and K will be, say, square root of n. Okay, once we prove this lemma, we have that every data structure computes in any square root of n-wise independent function must satisfy this. Okay, and how do we prove this? We can, for example, randomly sample vertices of the graph. So we sample each vertex of our graph with probability p, and p is gonna be square root of n over 2s. And I want to say that with non-zero probability, this set of vertices will span many edges. So since it's like non-zero probability, there exists such a set by the probabilistic method. OK, so what's the expected number? Simple means that this vertex remains in the graph only with probability p. What the expected number of vertices that are left in the graph? I started with s vertices, sample each with probability p, so it's ps, which is gonna be square root of n over 2. Then by some Chernoff, I'll have that with huge probability, the number of vertices is, say, from square root of n over 4 to square root of n, with probability all but negligible. Here, order of square root of n. Now let's count how many edges I span. So what's the probability that one edge is spanned? It's just, yeah, p to the t. Is p to the t, and this is supposed to be a nice expression. Let's see, this is square root of n over 2s to the power log of m over n based 2s over square root of n. So this is going to be n over m, right? That's the probability that one edge is spanned. So expected number of non-spanned edges is then m times 1 minus n over m minus n. And then by Markov, probability that the number of non-spanned edges is at least m minus square root of n is at most m minus n divided by m minus square root of n, which is bounded away from 1. Say less than 1 minus 1 over m. OK, so what do I have now? With non-zero probability, with probability at least this 1 over m minus whatever Chernoff gives me, which is still non-zero. I have that the number of spanned edges is greater than square root of n, and the number of vertices that span them, the number of selected vertices, is at most square root of n. OK? So we proved that with non-zero probability, a random sample works, so there exists a set of a few vertices that span many edges.
And why is this a contradiction to the existence of a data structure again?
Yeah, so that means that I can find a few memory cells that are sufficient to answer many queries. And this can't happen for a k-wise independent function, for say square root of n-wise independent function. Why is it so? Because look at this set of square root of n outputs. Since they're independent, that means they can in principle take all f to the square root of n values.
Mm-hmm.
But from only square root of n minus 1 elements, you can in principle generate only f to the square root of n minus 1 values, which is smaller than this. So you don't compute this function correctly. Okay, any questions about this? This lower bound is going to be important for us.
So when it's actually root n-wise independent, does this bound?
No, like we don't really need square root of n-wise independence, of course. Like even smaller independence would do.
I mean, the right-hand side.
Here?
It's always it's always at most a constant, because S is at least n.
S is at least n, yes.
So and M is also poly n. So the bound is always a constant if it's only root n.
The denominator seems to be.
Oh! I shouldn't have written square root of n. Oh, sorry, got it. Yeah, it should be n.
I guess we n over polylog y.
Yeah, n over something very close to n.
Yep. That's a good point. Sorry, I just wanted to simplify the calculations, and that.
You know, you could just put k, I guess, if it's k wise independent. Then you get
Yeah. All right. Yeah, that's a good point.
Wait, so could you clarify the point that we just?
Yeah. So in the actual bound, I should have n here. And the same proof would go through. Just the calculations would be slightly amiss here. Yeah.
You have 2s by k there, right? K, if it's k wise independence, you get 2s by k. K would be like n over log n or something.
Yeah. You can take n over log n wise independence. Yes.
So you
Yeah.
use a log in the.
Yeah.
I have a question. So suppose this that function you chose was linear.
Yeah.
Then I guess the same thing would go through if we just make it linearly independent, right? I mean,
Sure, it's the same thing
Same
for
thing.
linear function. Yeah.
But so is there an example where you have a function which has this k-wise independence?
That is not
and
linear?
You do it. You have a data structure of this size.
Is there a k-wise independent function for which we have such an efficient data structure?
Yeah.
No, I don't know such a problem.
Yeah, I think so it's possible that just this property alone guarantees that it's.
No, Huaqing's example.
Yeah.
polynomial
So if you sample a random matrix, so the problem is defined by a matrix of n by n, right?
Mhm.
If you sample a random sparse matrix with sparsity equal to this k, like this t, you have t non-zeros in every row or something. Then this problem naturally has a t query time data structure, but just wait, is that right?
Well, that's not type, right?
Yeah. Okay. What I want to say is that if you use a random data structure that's formed with query time t, where t is set to that number, I think it's actually the problem you're solving is actually k-wise independent with hard logic.
I see.
I guess I need to double check, but I had this impression that.
So there is like this bound is tight in the following sense. Like using this technique, you can't prove better lower bound because a random graph with for every t which is greater than this. There exists a T uniform hypergraph with S vertices and M edges, such that for every K and for every K set of vertices, it spans like fewer than K edges.
That will show that the proof technique is.
Right. It cannot
but
give
it
you.
can still be the case that.
Yeah, maybe.
Some other property.
Mhm. Sure. I'm just saying that this.
You have to argue that your data structure does not induce an expander or a hypergraph. Otherwise, right? I mean, cell sampling will fail for expanders. Fail to give you something high.
So in some sense, this lower bound can be a tiny bit improved, actually. So this is a function of two parameters, t and s. When you write it as the other way, like if you write this bound in terms of s, then we have this lower bound. S is at least n times m over n to the 1 over t. And a random graph would not say that this is exactly tight. This bound can actually be improved to, the same proof technique would give you this bound, and it can actually be improved to the following expression, which is tight again by the random graph. Why could we care about this improvement? For example, for the following reason. So recall that every data structure has two trivial solutions. Every data structure problem has two trivial solutions. One is s equals m, t equals 1, and another one s equals n, t equals n. We can't prove any interesting lower bounds in general, but can we prove strong lower bounds for small values of t? For example, when t equals 1, you can only read one memory cell. It's not hard to show that, for some problems, S must be essentially M. The space that you, this is the only data structure. Can we prove such a strong lower bound for t equals 2? So the standard, the cell sampling bound doesn't exactly give you this. It gives you square root of M. This improvement gives you this. It gives you that S must be actually M times 1 minus little of 1. So for example, and it also works for k-wise independent functions. So for example, no data structure with t equals 2 can compute k-wise independent function unless you essentially precompute all answers in advance.
Does this lower bound work in an adaptive?
No. This lower, so a cell sampling lower bound, the previous one, can be generalized to adaptive data structures. This we don't know how to generalize. I can sketch this, say, proof. So here it's interesting that random sample of memory cells or random sample of this vertices in the graph doesn't seem to give this. So we imitate it deterministically, essentially. We find a better deterministic choice of the vertices. So what? Let me remind you what we want to say. We want to say that in every two uniform hypergraph, that is in every graph, on S vertices, and say, for simplicity, I'll have some gap here, 3s over 2 edges, there exists a k set of vertices spanning at least k plus 1 edges for small k. If we prove this, then we prove that even 4 log n wise independent function requires linear lower bound on S when t equals 2. Okay? Does it make sense? Yeah, how can we prove this? We'll use the following simple claim. If you have a graph on S vertices of mean degree delta at least 3, then for every vertex v, there exists a tadpole graph starting at V and of size less than 2 log s. Here's what a tadpole graph is. It's a path, possibly empty, plus a cycle. Okay? The claim is just trivial. I'm just drawing BFS tree from the vertex V. Since mean degree is 3, if I don't have back edges, then my branching factor in the tree is at least 2. So I keep going until I see a back edge. But then the depth of my tree is at most log s, because the mean degree is 3, so branching factor is at least 2. And after at most log s levels, I will see a back edge. And this gives me tadpole. So here is my path, and here is my cycle. The depth is log s, so total number of vertices or edges in the graph is at most 2 log s. Okay? Now we can prove this lemma, that if the number of edges is at least 3s over 2, then there exists a k-set of vertices spanning more edges. How do we prove this? We say, look, just by the bound on the number of edges, average degree is at least 3. So I can find a subgraph of minimum degree at least 3. How do I do this? I just remove vertices of degree 0, 1, 2. Average degree is growing. At some point, all vertices will have a degree at least 3. So I have a cubic subgraph. Now I can apply this claim. I find some tadpole. I contract the cycle in one vertex, apply the claim again from this vertex. I'll find another tadpole from here. And that's it. Because if you look at this path and a cycle, then the number of edges in such a graph is greater than the number of vertices. Each tadpole is of size 2 log s, so I found a graph of size 4 log s. In fact, I could say something more. I could say like k plus 2 edges, if I replace it by 6 log s, by just adding one more tadpole, right? I can increase the gap between the number of vertices and number of edges. And this is useful because this actually allows us to generalize this bound for every value of t. Let me show you how we for free get a bound for t equals 3. Say we'll prove as is at least order of square root of m when t equals 3. So in this case, what do we want to prove? We want to prove that every 3 uniform hypergraph with many edges also contains a set of vertices spanning more edges. So we want to say for every 3 uniform hypergraph on S vertices and M, say at least S square over 2 edges, there exists a set of k vertices spanning k plus 1 hyperedges. And k is small. If we prove this, we prove a lower bound on S. S must be at least square root of m, even when t equals 3. So how do we prove this? We say, okay, I have that many edges, so the sum of all degrees in the graph is at least 3s squared over 2. So there exists a vertex of degree 3s over 2. There exists some vertex, let me call it V. Now let me take the link graph of this vertex V, which means the following. I take all vertices except for the linking vertex. And my edges are now two uniform edges, like regular edges. I have edge x and y if and only if x, y, and v was an edge in the original graph. So if in the original 3 uniform graph that was my linking vertex v, I had edges x1, y1, x2, y2, x3, y3, all with v. Then in the new graph, I'll connect sy and y1, x2 and y2, and x3 and y3. So I have this graph, 2 uniform graph, whose average degree is at least 3. So I can apply our result for t equals 2. Find a set of vertices that spans at least k plus 2 edges. Now I add my original vertex v, and together with it, I span at least k plus 2 edges in the 3 uniform hypergraph. So I found a set of k plus 1 vertices in the 3 uniform hypergraph spanning at least k plus 2 edges. And this extends to larger values of k. Just we can always decrease the uniformity of graph by one by looking at a link of some vertex.
Is this tight?
This is tied by for this proof technique in the sense that I mean this claim is tight. Yeah, random graph says it's tight.
But for the constant query, you don't know that.
For constant t, I mean, like this shouldn't be a tight bound. A random problem should require still order of m here. We don't know how to prove it. This technique of kind of self-sampling will not lead there. So, okay, any questions about this? Okay, so
just to make sure.
Yeah.
Before you said it's tight, and then you improved it a little bit. And now
So
you
yeah, it's
so it wasn't completely tight, and now it is.
There are two ways to write self-sampling bound. One is as a function of s, one is as a function of t. T is at least log of m over n divided by log of s over n. Can be proved by sampling a random set of cells, and this is tight up to constants here. Now, if you sample a random set of cells, you'll get same bound in terms of t. It will be n times m over n divided to the power 1 to the over t. S, yes. Same bound, but written in terms of s. So this is not tight. Here you can actually improve it to this. And this is tight, yeah. Okay? Okay.
Do we know any examples, going back to the main theorem that you just proved?
Yeah.
So, let's see, I want an example where this mapping has high high k-wise independence,
Yeah.
very close to n, where there is a data structure that
That matches it. So In terms of data structures, I'm not sure if we have much in data structures, but we'll see that this is like morally equivalent to the question of matrix rigidity. And there we do know that this bound is tight for certain error correcting codes. So I assume probably by this connection we can maybe say that it's tight for some error correcting codes for data structures, but yeah, Kasper, you have...
Yeah, I'm just thinking that that's what Hutchin was trying to say before, right? That if you just pick a random matrix that's basically this sparse, that it will correspond to something that's...
it will give you some code with related parameters?
But you could always have a data structure that just doesn't store anything, it just reads the things it needs to sum up.
Yeah, I think
that's
like,
what Hutchin was trying to say.
For poly n by n matrix with all of log n non-zeros in every row, if we pick a random such matrix, remember it has full rank, so which means it's n-wise independent. And then for this data structure, you have a space n data structure, just store the inputs, but then the query time is O of log n because each query only depends on O of log n.
And what's the independence of this matrix? So
with high probability, it has full rank, so it's n-wise independent.
No, full rank is
That's
different.
no, but I think you can still prove like n over log n wise independence.
I'm not sure you can prove it for... So Anna and Emmanuel, they work hard to prove that ECC can be factored into such sparse matrices in constant depth. But one sparse matrix, I don't think it gives you a good parity check. So it is full rank, of course, yes, but that's not sufficient for k-wise independence. For k-wise independence, you need to say every set of order of n rows are linearly independent.
But is that is that equivalent to full rank?
No, of course not. What if my matrix is full rank here and below all zeros? That's not k-wise independent, but it is full rank. The first n.
Sorry.
So I don't.
Yeah, you lose. Yeah, but in any case, remember the polynomial evaluation problem, right?
Whatever.
It's n-wise independent, right?
Sure.
And okay, I don't know if that's fair or not. There's a log n lower bound by what Hutchins showed.
Yeah.
And there's a log squared upper bound.
Yeah,
it's
yeah,
not
it's not
linear. I don't know if it's linear or not.
No, it's not linear and it's log square. Yeah.
Actually, is that true that if such a matrix, every set of all of n rows is linearly independent?
N over log n. Yeah, you
n
use
over
a log n.
Oh,
Yeah,
yeah,
you do
n
that.
over log n.
Yeah.
Yeah, I guess, but that would not be explicit. Oh, I guess you can do it explicit by error correct. Yeah, you're probably right.
Wait, so can you summarize where it is constructed?
In short, for data structures, I don't yet know an efficient data structure for ECC that matches this bound. But perhaps we can get it. I don't think sampling just a random matrix would work, because for matrix rigidity, we have to work to get such a ECC.
What is error correcting?
Error correcting code, I mean, yes. Yeah, there was a short note by ZF Dwyer saying that there exist error correcting codes for which you cannot improve matrix rigidity essentially over the cell sampling bound. And I think this might translate to the same statement for data structures. I never did it. Yeah. Never checked it.
So that would just to, so you're saying therefore that would mean that
Just k-wise independence might not be sufficient for proving stronger lower bounds. This is known for other primitives like matrix rigidity, and we suspect it should be the case here as well.
So you're saying for the van der Waals matrix, it's not known?
No, I don't think so. I don't think we have like tight. We do have diagonals, but yeah, that's different. Okay. Sorry. Okay. So we proved a lower bound in the strongest model, in the cell prop model, and say we proved a log n lower bound on C for linear space, and it clearly applies to weaker models as well. So we have this lower bound for all models. Now we want to understand, can we prove stronger lower bounds in weaker models or not? So the outline of the talk, so essentially what we'll see today is that here it will be hard to prove stronger lower bounds, here we will actually prove stronger lower bounds.
So when you say easy, it's not easy, but like,
doable. Yeah. Okay. So if we want to prove a barrier here, then for these two models, then it's sufficient essentially to prove a barrier here. And if we want to give a lower bound for these two models, we'll give a lower bound for the stronger model. So before the break, we'll see barrier for linear lower bounds. After the break, we'll see actually data structure lower bound for the group model, which also extends to semi-group model. Okay? So let's start with a barrier saying that, yeah, the current techniques, with current techniques, it should be hard to significantly improve on the cell sampling lower bound in these models. So this barrier is coming from the area of circuit complexity. So let me quickly introduce the main notation from this area. So we'll only be talking about computing Boolean functions from n bits to n bits. We're going to be computing them by straight line programs. That means no branching at all. You just run it line by line. Every line is a binary Boolean operator of the previously computed things or the inputs. So such a straight line program can always be also drawn as a directed acyclic graph, which is called a circuit. And so formally we have inputs, x1, xn, we have constants. Gates can compute any binary functions. And fan out of every gate is unbounded. Okay, so that's what a circuit is. Once again, we're talking about functions from n inputs to n outputs. We know just by counting that almost all functions require circuits of size 2 to the n. We also know a matching upper bound. Every function can be computed by a circuit of size 2 to the n. And so here is the state of the art. We know that almost all functions require exponential circuit complexity. If we could find just one function from, like, say, NP that requires just super polynomial circuits, then we would resolve P versus NP. And the best what we can prove is just like 4.1n, proven a year ago by Li and Yang. Okay, so that's the state of the art. Almost everything is exponential. We want super polynomial. We can only prove low linear lower bounds. And we have even for functions from much larger class, for functions from e to the nt. So we have many candidates for functions that require super linear circuits. For example, we now know how to multiply two integers of length n by a circuit of size n log n. And perhaps this is tight. We just don't know how to prove tight lower bound. Or say FFT, we know how to do it in time or by a circuit of size n log n. Maybe that's tight. We just don't know how to prove a matching lower bound. Many very simple functions like shifts of the inputs or permutations of the inputs are also conjectured to require superlinear size circuits. Or perhaps just pick your favorite NP-hard problem. Most likely it requires circuits of superlinear size. So we have many candidates. We just don't have techniques. We actually probably don't have techniques for proving superlinear circuit lower bounds. Right, so the techniques, huh?
Isn't like natural proof barriers?
There are even, natural proof barriers doesn't distinguish between linear, superlinear circuit lower bounds. There are other techniques that say that, our only way of proving circuit lower bounds cannot lead to lower bounds of greater than, say, 10n.
What is that? Yeah, don't tell us the details.
Yeah, so in this model, unbounded depth circuits, the only way we know how to prove circuit lower bounds is called gate elimination. And for this technique, we know how to prove that no gate elimination can give you better than, say, 5n lower bound, circuit lower bound. Yeah.
What's the reference for that?
That's a joint work with Sasha Smile, Sasha Kulikov, and Suguru Tamaki from some 5 years ago. So. Okay, so we don't have techniques to prove interesting circuit lower bounds. So what do we do in such a case? We consider some restricted class of circuits. Another natural parameter for a circuit is its depth, the longest path from an input to an output. So how about we look at circuits of logarithmic depth? If depth is less than 2 log n, we know how to prove strong lower bounds. We have functions that cannot be computed by circuits of depth less than 2 log n. But already for depths like 3 log n, we know nothing better than that for a circuit lower bound. So the current challenge, I mean, it was posed in the 70s, but still the current challenge is to prove superlinear circuit lower bound even for log depth circuits when the depth of your circuit is order of log n. Good thing about this question is that here we at least have an approach that we didn't rule out. We have a kind of combinatorial approach suggested by Valiant in 1977. Valiant proved that if you have a linear size log depth circuit, then the same function can also be computed by the following depth 2 circuit. You have n inputs, you preprocess them into epsilon n memory cells. So here your preprocessing loses some information, so I cannot say that every output looks only at memory cells, because this preprocessing loses some information. I have to say that outputs look at the memory cells and inputs, but luckily I can say that they don't read many cells or inputs. So Valiant said that if your function can be computed by a linear size log depth circuit, it can also be computed by such a depth 2 circuit or such a data structure. Okay, so if you find a function that cannot be computed by such a thing, a random function cannot, then you prove a superlinear circuit lower bound for log depth circuits. Okay?
Candidates for that?
Yeah, all of our standard.
Candidate rigid matrices, you'll get to that.
Yeah, but I mean, we need candidates for rigid matrices as well. But even like Vandermonde, Hadamard, error correction codes, they all are candidates here.
No, I think I got confused. So what was Valiant's proof if you have a linear problem?
Linear size? No, there is nothing linear so far. Linear size circuit.
Okay.
Then you can also compute it by such a thing. Log depth. Yeah.
Linear size.
Yeah.
Then I can compute it with what? Is this linear or there is no linearity?
Only for rigidity and only for one valence question.
I think I was just saying that just showed that the Hadamard actually has a small thing like this, right?
It is not that small,
It,
right? Yeah, non-trivial rigidity, but not
Okay.
that small.
No, I mean it. So
Okay.
Valiant posed 2 questions about rigidity. Josh proved that Hadamard matrix and like some follow-up works extended to other matrices doesn't have rigidity. It doesn't say much about the specific structure. And second, Valiant actually asked 2 rigidity questions. The other one has weaker rigidity parameters, which would still allow us to prove some circuit lower bounds. That is not ruled out for Hadamard or any other matrix. Yeah. Sorry, someone had a question, I think.
So
Yeah.
here, this is also not linear. There's no
Not yet. We will make it linear soon, but so far, no. This is true for all circuits. Yeah.
Just to summarize, you take a log n depth circuit and compress it to depth 2 with this advice in the middle.
Exactly. Yeah. Yeah. Well, this is also sometimes called common bits. Every output can take a peek at it. Yeah. More questions? Okay. Okay. So this is an efficient data structure. This is a small circuit. So there are some differences. Efficient data structure has more memory cells than n, s is greater than n, but every output looks only at memory cells. Small circuit preprocesses it into fewer than n bits, but every output looks at the memory cells and inputs. So these pictures are very similar. We would like to say that they're the same in the sense, like if you can prove a lower bound here, it would imply a lower bound there, and the other way around. And we don't know how to do this.
Isn't it like a systematic succinct data structure?
Yeah, it is. Yeah, it is. It exactly is. Okay, so we don't know how to prove equivalence of these 2 pictures. What we can do, though, we can prove essentially equivalence of these 2 pictures for the case when we're solving linear problems by linear data structures and linear circuits. And I'll sketch this now. So we'll work with linear problems. What does it mean? A problem is just given by a matrix. Then for every input vector x, you need to output m times x. This is a rectangular matrix, which is tall. It has many outputs. It has fewer inputs. For every vector x, you want to just output m times x. So what does it mean now? Let's look at the valence result and see what we have when everything is linear here. So each of these functions is a linear function of the inputs, and each of this function is a sum of linear function of the inputs and a linear function of memory cells. So each of these maps can be written as a matrix. So if you compute matrix M, I can say that in some matrix A, I just write the dependencies of outputs on the inputs. Then matrices C and D encode the dependence of outputs on the memory cells and of the memory cells on the inputs. Since all computations here are linear, I'll just write it in a matrix form. So if you have a small, say, linear size log depth circuit, which is linear, then you can also write your matrix computable by the circuit as A plus CD. And note that A and C are sparse because they decode the dependence of outputs on inputs and the dependence of outputs on memory cells. They look only at a few positions and some T positions. So these two matrices are sparse. So I can also write it as a sum of sparse matrix and a low rank matrix. The product of these two matrices is low rank just because the inner dimension of the product is small. It's epsilon n. So the rank of their product cannot be larger than epsilon n. Okay? And this actually brings us to valence definition, Grigoriev's valence definition of rigidity. We say matrix is...
So the sparsity of C was not important, right?
Not yet. Later we will actually use it. Yeah, we'll actually use it for one of the connections between data structures and circuits, but it's not important for, say, matrix rigidity. Matrix rigidity ignores the fact that C is sparse. Yeah. So matrix is rigid if it cannot be written as a sum of sparse and low rank. It's epsilon n T rigid if it cannot be written as a sum of matrix of rank at most epsilon n and a T sparse matrix. And in this talk, whenever I say a matrix is sparse, I mean it's row sparse. T sparse means every row has at most T non-zeros. Okay? Once I have a sparse matrix, it cannot be written this way. So it cannot be computed by such a depth 2 circuit. So it cannot be computed by a linear size log depth circuit. If we find a rigid matrix, we prove a superlinear circuit lower bound for log depth circuits. Okay? So okay, this is what happens to circuits when we're considering linear circuits. Now, what happens to data structures when we restrict our attention to linear data structures only? So this is our data structure. Now we say all memory cells compute linear functions of inputs. All outputs compute linear functions of memory cells. Again, I can encode it as product of two matrices. So efficient data structure means my matrix computes a matrix M if and only if it can be written as a product of two matrices. One of them encodes the dependence of outputs on memory cells. The other one encodes the dependence of memory cells on the inputs. This one is sparse because that's how many memory cells each output looks at. So every row is T sparse. And this matrix is actually small because recall that we're working, say, with n to the 100 queries. This is a huge matrix, n to the 100 by n. This is n to the 100 by s. And this is just s by n. Say we're working with in the linear space regime, so s is order of n. This is just n by n matrix, while the original one is n to the 100 by n. So this matrix is really small if you compare its size to the size of the matrix n. There exists an efficient data structure if and only if the matrix can be factorized as a product of sparse and small. Make sense? Okay, so now again, small circuits or non-rigidity means you can write your matrix as sparse plus low rank. Small data structures, efficient data structures, means you can factorize your matrix as a product of sparse and small. So what we do in this work, we essentially prove almost equivalence of these two representations of a matrix. Okay? So let me show you one connection between these two representations, just how in general we can go from, say, data structure lower bound to matrix rigidity lower bound, and then I'll mention what else you can get using same ideas. So I'll need just some prop. Yeah.
This m equals k times
Yeah, that's equivalence.
But
And
the other one is not.
other one is not. We don't know. We don't know if a non-rigidity is equivalent to small circuits. Probably it's not. But yeah. Okay. Okay. So I want to show a connection between rigidity and data structural outer bounds. For this, I'll prove some structural property of non-rigid matrices. So look, a random matrix is rigid. Being rigid is kind of natural properties. Most matrices are rigid. If you are not rigid, there must be a reason for it. So there must be some structure in your matrix. Here is one structural properties that we prove. One structural property that we prove for non-rigid matrices. Say M is a full rank matrix. It's essentially without loss of generality. If you give me a matrix which is not rigid, then I'll find a sparse matrix of same size, which is essentially as good as your matrix. My column space will be very close to your column space. You give me possibly a very, very dense matrix, which is not rigid. I'm drawing a matrix of same size, but my matrix is sparse, and its column space is almost the same as the column space of your original, possibly very dense matrix. Okay? So let's prove this lemma. Assume M is not rigid, so it can be written as a sparse plus low rank. Now let me define a linear operator whose kernel is exactly the column space of M. There are millions of such operators. I pick just any of them. So column space of M is just some subspace. I pick any operator whose kernel is exactly the subspace. Okay? Now I apply this operator to this equation. I get Lm equals La plus Lb. But L was defined exactly in the way to kill M. Lm is 0. That's essentially the definition of L. So I have that La equals minus Lb, or in particular, rank of La is the same as rank of Lb. B was a low rank matrix, so Lb is definitely a low rank matrix. So what do we have now? A is a sum of full rank and low rank matrices. By subadditivity of rank of A is huge. I start with a matrix of almost full rank, apply a linear operator to it, and get a matrix of rank almost 0. How could that happen? That exactly means that the kernel of my operator is very close to the column space of the matrix I'm applying it to. The column space of A intersects the kernel of my operator a lot, in at least n times 1 minus 2 epsilon dimensions. Which, again, by the definition of L, just exactly gives me that intersection of column space of A and column space of M is huge.
This is called inner dimension or something?
It will be called soon, yeah. Yeah. Okay, so if a matrix is not rigid, I can find a sparse matrix whose column space is almost the same as the column space of the original matrix.
Does the row sparsity matter here, or it just needs to be sparse?
Does the row sparse? No, here it doesn't matter how you define sparsity. Okay, so let me prove one connection between data structural outer bounds and rigidity. I'll just say for every matrix, either it has super efficient data structure with space just 1 plus epsilon n, or it contains a rigid matrix, a rigid submatrix. Okay? In particular, you can read it as follows. If you have a data structural outer bound for this matrix, this doesn't hold, you get rigidity. Data structural outer bound implies rigidity. Okay? Okay, so how do we prove this? We start with a matrix, M. And now, if it's rigid, I'm done. It contains a rigid submatrix. So assume it's not rigid. Then I have the structural property. I have a sparse matrix that generates a constant fraction of the column space of M. So in particular, I can multiply the sparse matrix to generate a constant fraction of the columns of the original matrix. I can multiply it by something and get exactly these columns, just because I generate almost all of the column space of the original matrix. Okay, so I have a T sparse times a small matrix that generates almost all of my original that gives me almost all of my original matrix. So recall that this is exactly the definition of efficient data structure. I just got an efficient data structure for like 99% of my original problem. Sparse times small is exactly an efficient data structure. Okay, I still have some yeah?
So I will get this matrices AB.
So I start with this matrix. If it's rigid, I'm done with the proof. If it's not, we just prove the structural properties. There exists some sparse A.
Structural property is the previous.
Yeah.
I see. Okay.
Such that its column space generates a huge chunk of the column space of this matrix. In particular, I can multiply it by some matrix and get most of the columns here. This is efficient data structure for 99% of my original problem. Now I just recurse here. Either this submatrix is rigid, which is good, I'm done, or I will find another efficient data structure for another 99% of this problem. And I'll keep going for some log n steps. That's why I'm losing some log n here in the parameters. I keep going until I have such a tiny data structure problem that I can just solve it by a trivial data structure. So either at some point, I'll find a rigid submatrix, which is good, I'm done, or in the end, I combine these data structures together to get a data structure for the original problem. Make sense? Yeah.
So what about the size of n prime?
What about n prime? Yeah, so Anna says normal people define rigidity for square matrices. Why do you, Sasha, define it for rectangular? Yeah. So we have some bounds, but it's not going to matter. Later I will show you that actually from this rigidity you can get a good square matrix of like n by n size essentially, which is rigid. So it doesn't matter how, what is the shape of the rigid matrix that we find.
I wasn't worried about the shape. I was worried about the size.
Okay, n prime will be like polynomial in n, if that's what you mean.
So it will be large.
Yeah, it will be large, yeah.
So it's not completely explicit, right? It's more like saying...
Yeah, that's a very, very good point. The submatrix that I find is not in class P. I cannot find it in polynomial time. I can find it in P to the NP. That is, in P with an NP oracle. But for circuit lower bounds or matrix rigidity, even getting a lower bound for E to the NP is a big open question. Here, our matrix is not in P, but much better than in E to the NP. It belongs to, our submatrix is in P to the NP.
So wait, where do you need it?
I need to check if this original matrix is rigid. That's NP hard problem. With NP oracle, I do it fast. If it's rigid, I found it. If it's not rigid, then I find this factorization essentially. I need to get this A, which is a witness that my matrix is not rigid. Again, I can use NP oracle for this, okay, co-NP oracle, but they're the same. Yeah, that's a very good point. The submatrix is not completely explicit. We can find it in polynomial time with an NP oracle. Okay, so to formalize what we did, we need two definitions. For sparsity parameter T, we say the outer Paturi-Pudlik dimension of the matrix M is the smallest number of columns you need in a sparse matrix to generate the column space of M. So you give me some possibly very dense matrix. You want me to generate all of its column space, but by a sparse matrix. Perhaps for this I need more than you have columns. So the smallest number of columns that I need for this is called Paturi-Pudlik outer dimension of the matrix. And the inner dimension is kind of the opposite thing here. Now I can only use matrices of the same size. They must be sparse. What's the largest chunk of the column space I can generate? What's the largest fraction of the column space of the original matrix I can generate by sparse matrices of the same size?
There's some duality.
Huh?
There's some duality.
There are some connections about them, between them, and that's actually all what we do in this work, because apparently outer dimension is exactly equivalent to efficient data structures. A problem admits an efficient data structure if and only if its outer dimension is small. And rigidity is exactly equivalent to inner dimension. A matrix is rigid if and only if its inner dimension is small.
Sorry, can you go back to the definition of
Yeah.
I think a picture might help. One of them you want to contain the entire column space. The other thing, I give you a budget of
Exactly, n columns. Same.
n column, and you're trying to cover as much as you can. So a picture would.
All right, so a small outer dimension is exactly equivalent to efficient data structures, and a small inner dimension exactly equivalent to rigidity. And in fact, all what we do in this work, we prove a bunch of relations between outer and inner dimension, which establish all the connections between rigidity and data structure. So for example, what we proved on the previous slide, data structural lower bounds implies rigidity. That was actually a statement about outer and inner dimensions, as you well pointed out. Yeah, we actually proved that if outer dimension of a matrix is small, then it contains a submatrix M prime with small inner dimension. And as a corollary, we get that any like data structural lower bounds imply rigidity. In particular, if you can prove super log square lower bound in the data structure world, that would imply a new rigidity bound for rectangular matrices, better than we know. And we can also say that if you prove a better than log cube lower bound for data structures, that would even imply new matrix rigidity lower bound for square matrices, which is like the main question in matrix rigidity.
This is only one way though, like you're not.
So far. That's one connection between outer and inner dimension. We can prove something else. We can prove their sum is always at least 2n, which is maybe what you meant by duality. And this in particular gives us that rigidity implies data structural lower bounds, and actually here we do not lose anything in the parameters. Previously we lost some like local log square factors. Here we don't lose anything in the parameters.
Do you think it's possible not to lose the log n?
So, yeah, maybe. I don't know how to do, yeah, maybe. We also prove like other connections. Say if you prove, a large outer dimension implies circuit lower bounds directly. And this actually uses the fact that Arkadiev pointed out that in this factorization, invariance factorization of matrices, variance ignores the fact that another matrix is sparse. If you take it into account, you can prove such a statement. Large outer dimension, not necessarily rigidity, just outer dimension, would apply circuit lower bounds. And in particular, this tells us that very strong data structural lower bounds would even imply superlinear circuit lower bounds. And there are more connections. I'll just list them here. So it looks like there are some connections for succinct data structures and so on. It essentially, these bounds essentially match the best known lower bounds for data structures and matrix rigidity in all the settings of the parameters. So they both have this S and T, two parameters, so you can work in different settings. And so it shows that our current best lower bounds in data structures and in matrix rigidity kind of correspond to each other via these connections. Or in other words, our connections didn't lead to any new lower bounds. Yeah?
Are the rigid matrix and the data structure that's hard like equally explicit, or is there also like something implies a p to the p?
No. So when we go from data structure lower bound here and here, only in the first two things, we get p to the np. Everything else is as explicit as in the premise. Yeah.
How does it relate to your result with
Josh recently, together with Liji Chen and later follow-up work, they showed a matrix, say in p to the np or fnp, that is rigid for very large sparsity parameter, essentially n square, and rank, which is 2 to the log n to the 1 minus epsilon. This is rank. Sparsity is essentially n square, and you can construct it in fnp or p to the np's.
And that doesn't give any data structure?
It doesn't seem to give any data structure.
So I have a question. So for example, for the data structure problem, you want to store a matrix and the query as a vector, and you want to compute matrix times vector.
Matrix defines the problem. You can store whatever you want, and you want to compute a matrix times vector. Oh, sorry.
No. The problem is matrix multiplication.
Okay.
So you want to store a matrix. Is that what I don't know if that's what you mean by matrix defines the problem, because here it's a little different, right? So you want to store a matrix, and the queries are vectors of n bits. And
Yeah.
you want to do a matrix vector.
Yeah.
Now, so you can conjecture, it's reasonable to conjecture that you need to, you need log n, you need n square time.
Mhm.
Because you need to read the entire matrix.
Yeah.
No matter kind of how
Yeah.
it's stored. Or, n squared by log s or something. Now, that's exactly, in this parameter, this n squared is exactly log square of n.
Yeah.
Right?
But that doesn't exactly fit in this framework, because output to a query is not a linear combination of the inputs.
I understand.
Uh-huh.
I understand. But still, this seems to be, the upper bound seems to be below the threshold. So you could hope that you could, you could say even if there was some kind of similar barrier there,
Mhm.
you could still prove the lower bound of n squared, which is what you want, because
Yeah.
it doesn't go beyond this
Yeah.
log n
Yep.
squared.
Yep. I agree.
So, but would you get something like if you prove omega of log to 1.9?
This we don't yet know. Yeah. I don't know how to improve our lower bound so that we don't lose a log n here. Yeah. No.
So you get no rigidity whatsoever?
No.
Even weak?
No. No, I mean, you get rigidity that we already know how to get without it.
Oh,
Yeah.
I see.
Yeah. I mean, essentially, no. What's happening here is that if you get C is at least something, then I get rigidity C over log n, but I know how to get rigidity log n. So it's only interesting when C is super log square.
But the log n you lose because you have log n levels.
You had a slide
Maybe it's possible
Yeah.
to avoid
which showed the relationship between inner and outer dimensions.
Between inner and outer dimensions, yeah.
What do you know? What are your theorems? Can you summarize?
Yeah, so we prove, say, three relations. One is this. If outer dimension is large, there exists a submatrix with small inner dimension. Moreover, submatrix is reasonably explicit, P to the NP. Another one, sum of the two quantities is always at least 2n. Third one is that outer dimension is sufficient for circuit lower bounds. You don't have to get rigid. Yeah, outer dimensions are sufficient for circuit lower bounds. This is three statements about inner outer dimensions, which which are sufficient to prove all these connections, because outer dimension is exactly small data structure, inner dimension is exactly
So for
rigid.
the first result,
Yeah.
do you have any notion of this is best possible in some sense?
No. We're losing log n factor. We don't know how to overcome this, but yeah, there is no reason to think you have to lose the log n factor.
So,
Yeah, I'll mention one thing and we'll do the break. Yeah.
so all these results are for linear problems. So do you
And
know
linear
that-
data structures and
Yeah,
linear
yeah.
circuits.
Yeah.
Yes.
So do you know any barrier for, like, if I prove a high static low bound for some nonlinear data structure?
No. So first of all, yeah, it's not. First of all, if you prove, say, log to the 1.5n lower bound, that would be a breakthrough, I think, in data structures, and we have nothing from it. That's one thing. Second, maybe for non-linear problem, you can still prove self-prop lower bounds. You cannot prove them in the linear model, of course. We don't have any implications of this. And finally, like, improving this rigidity a little bit is not such a big deal. It wouldn't. We couldn't. We didn't do it in 50 years, but I mean, it wouldn't imply any new circuit lower bounds or something. So that's a kind of barriers of current techniques, but still, I think that might be doable. Mm-hmm. Yeah.
I missed what you said earlier also, like log to 1.5, like why would that be amazing? I mean,
No, just for data structure lower bounds, it would be amazing to prove a lower bound but higher than log n.
I thought there is some log squared.
Only for dynamic.
For dynamic, yeah. For static, anything better than log n would be great.
Matrix vector problem, like, do you think that n is...
Matrix vector product doesn't fit in this framework.
No, it kind of does, because the query is y, right? So each query is actually linear. a linear function of the matrix entry.
Not quite. You have too many outputs per query. Like output is not one element, which is linear combination of the inputs. And if you do it UMV, then it's not linear because it's quadratic form. Yeah. So it doesn't exactly fit in this framework. Yeah.
Wait, why UMV is not?
So what's the query you
query is a pair UNV.
Yeah.
The input data is this n by n matrix. So it is.
Yeah, it's just the sum of the entries in the rectangle generated by UNV.
Yeah, no, that's true. That is linear. That's a good point.
It's just the outer product of UNV gives you the subrectangle, or no? Am I seeing this wrong?
No, it's right.
Oh, you're saying that UNV define but then I see the output is just
exponentially many queries.
Yeah. So there in UMV we usually view it as some line problem, which means, I mean, yeah, the possible number of queries is exponential.
Right.
In which case, lower bounds are easy to prove. Like you can prove lower bounds which are like log of possible number of queries.
Right, but now you want log squared.
Right.
Yeah. No, that's a good point. Yeah, that's a very good point. Yeah.
So proving log to the 1.9 would be essentially proving the OMP conjecture in some sense for a linear data structure.
I'm not sure it's.
Log number of queries to the one. Yeah, to something. Yeah.
And this would not imply any rigidity.
No.
Yeah.
Yeah.
You go back to this slide about this thing that about
That's it?
Yeah, just leave it there for later.
Oh, I wanna say one more thing before we go for break. So so the matrices that we obtain in these arguments are often rectangular, and for rigidity for circuit lower bounds, we often would like to have square matrices. So how do we go from rectangular rigidity to square rigidity? So a naive way would be, say this matrix is rigid. I just take a bunch of copies of this matrix together, make it a square matrix, and I would like to say that the resulting matrix is rigid. That is, that its say sparsity parameter grows proportionally to the increase in the size. Because we know about M that in order to drop its rank, say below epsilon n, you have to make t changes. If you want to drop the rank of the whole matrix below epsilon n, you have to decrease the rank of this submatrix, of this submatrix, of this submatrix. So you have to make t changes in each copy. So the sparsity parameter should grow proportionally to the increase in the size. Right? There is a problem that we work with row rigidity. T is the number of elements per row, like per row, row sparsity. That is, maybe to decrease the rank of this matrix, you need to change only t entries in this row. Here, only t entries in this row. Here, only t entries of this row in this block, and then total sparsity is still like it's t row sparse matrix. So the sparsity in this kind of rigidity doesn't actually grow when you stack a bunch of copies together. Mike, you look puzzled.
Yeah, I am puzzled.
So recall that we defined rigidity as kind of row rigidity. That means the matrix is rigid if the following holds. In order to drop its rank below epsilon n, you have to make t changes in at least one row. Now I stack many copies of M together, and I would like to say that the sparsity parameter in rigidity grew. But that's not necessarily the case. Maybe I can decrease the rank of this matrix by changing t entries in the first row, decrease the rank of this matrix by changing t entries in the second row, and in the third row.
Right, but that doesn't mean, but the composed matrix, why does that drop the rank of?
No, not necessarily, but how would you prove that rigidity is high? Usually you would say you have to make many changes here, many changes here, many changes here, because you have to decrease the rank of each copy. This doesn't work here, just because our notion of rigidity is kind of worst case rigidity, row rigidity. It would work for like global rigidity, where we would say matrix is rigid if in order to drop its rank below epsilon n, you have to make s changes in the matrix. then this kind of direct sum of course works, because you need to decrease the rank of each copy, so you have to make at least s changes here, at least s changes here, at least s changes here. So you would have this direct sum if you work with, not with row rigidity, but with global rigidity.
Do you have a counterexample to the top thing?
I think we had, and that's why I think, I'll take it offline, I think we had. And that's why instead we go from row rigidity to global rigidity, and for global rigidity, direct sum just holds. I'll just show you how to go from row rigidity to global rigidity, okay? And then you can get square matrix. Okay, so here is a theorem. Let me take any generator matrix of a good locally decodable code. If my matrix is row rigid, then its product with LDC is actually globally rigid. And so it was T row rigid. I would like to have rigidity T times the number of rows. I lose a little bit. I lose the number of queries made by LDC, but this is essentially log n. I'm losing another log n factor here, but go from row rigidity to global rigidity. One can view it as a worst case to average case reduction, because row rigidity says whatever low dimensional space you give me, at least one row is far from it. Global rigidity says whatever low dimensional space you give me, at least 10% of the rows are far from it. So what we're doing here is worst case to average case reduction for rigidity, and we're using worst case to average case techniques. That's essentially what people do when they prove that say circuit lower bounds in E would imply P equals BPP, this kind of things, another worst case to average case reduction. All right, so that's a way to go from worst case rigidity to global rigidity, and for global rigidity you can easily go from rectangular to square matrices.
A random question. So
Yeah.
if you start from a data structure that has average query time T instead of worst query time T, do you directly get global rigidity?
No, actually, I'm not sure. I'm not sure. Okay, so that's what we've done. We proved that we proved some barriers here for proving the stronger lower bounds here. There is still hope, but yeah, we proved some barriers. And after the break, we'll prove lower bounds for the group model. All right, let's take a break.